In this lesson, we'll continue with our review of memory using the example of learning about amoeba in a classroom. And initially we said we make a strong memory trace in the hippocampus with weak memory traces up in the cortex. It's the process of system consolidation then that is going to transform that memory, that cortical memory. It's going to strengthen the cortical memory so that that information can be accessed, in fact, without the hippocampus, as we saw in the case of HM. But this is also the way the brain is going to be integrating new information into the semantic memory system stored in the cortex. So we call this system consolidation, the reorganization of the memory involving the hippocampus and the cortex. And metaphorically, it's like the hippocampus is sort of teaching the cortex to make a hippocampal independent memory, a semantic memory of the information that was present in the episodic learning event. So here we're going to use sort of pictures, and the vividness of the pictures and the words here will represent the strength of the memory stored in the cortex. So initially, while we have a strong memory trace in the hippocampus, notice the concept of amoeba is kind of weakly stored. What amoeba look like, weakly stored. The sound of the word, weakly stored. So this is before consolidation. And after consolidation, we represent a stronger cortical memory by more vivid items here in the cortex. So before consolidation and after consolidation. And the question is then, how is the brain doing this? How is the hippocampus helping the cortex make stronger cortical memories? Scientists have recorded the activity of hippocampal neurons during learning, immediately afterwards, and even during rest and sleep. So now imagine we're in the lab and an animal has a learning experience. What scientists were able to do is to record from individual hippocampal cells during the learning episode and then after the learning episode, and even when the animal was asleep. So they could keep track of hippocampal cell activity at these different time periods after learning. And what they found was interesting. That after learning, the same hippocampal neurons that were active during the learning became active again. This replay, as it were, may help to transform the memory by strengthening the cortical memory trace. So we're going to call this hippocampal replay, and it occurs immediately after learning. And so the suggestion is, while these hippocampal cells were activated during the learning process itself, after learning, it's as if the hippocampus is replaying that memory trace. And that replay may help to strengthen the cortical connections for the cortical version of the memory trace. And scientists have lots of evidence that sleep has important memory function. Without interference from ongoing perceptual and cognitive activity, the brain can process recently learned information. And sure enough, this hippocampal replay has been detected during sleep. So the idea is sleep turns out to be, it's an ideal time to process memory. See, then you can kind of reactivate the events of the day without any interference from ongoing perceptual activity because you're unconscious. So scientists suspect that what's going on here is that during sleep, certain stages of sleep, the hippocampus is again replaying recently learned information, and that's going to help to strengthen the cortical memory traces for those events. Now, this consolidation process, which includes this hippocampal replay, can integrate new information but also strengthen the connections between already learned information. And so we'll add that sort of detail by showing the arrows here. Remember, the concept of an amoeba has access to what amoeba looks like and the sound of the word amoeba, etc. So consolidation can also strengthen the linkages between the aspects of concepts, in addition to inserting new information into a semantic memory. So the concept of an amoeba is more strongly stored and integrated into semantic memory as a result of consolidation. So before consolidation, after consolidation, these links are stronger as well. So at the level of synapses, so now we're showing sort of the cortical association areas here with individual nerve cells, and we got synapses there. At the level of synapses before consolidation, we might have a strong memory trace in the hippocampus, but weak synapses in the cortex, right? And then after consolidation, the idea is we have stronger synapses in the cortex. So the information about amoeba is better stored in the cortex as a result of this consolidation process. We have LTP happening at the cortical synapses to increase the strengths of communication between the relevant neurons, and so we're making longer lasting memories in the cortex. Now, let's consider the situation where we perhaps had a learning event with a microscope and we learned about amoeba at some point. But let's say later on we are reading about amoeba. And let's say we are reading that amoeba are single-celled. Maybe we didn't know that initially when we were looking at them on the microscope. So here we're noting that the circumstances of learning have to do with reading a book. That's a different kind of circumstance than being on the microscope. Okay, so now we're going to ask the question, so how does this new information, how can it be sort of installed in semantic memory? How can it be connected up with previously learned information? So the idea is that, remember, the hippocampus is good at pattern separation. In this new learning experience, if it's a different event, and so we've got different hippocampal cells that are making a memory trace of the new information that we're learning from the book. And that information is about being single-celled. And so because this just happened, we have a weak connection to the concept of an amoeba. It's newly learned information. The hippocampal memory trace might be strong, but the cortical memory trace is still weak. We haven't made a strong connection yet between the new information and the amoeba. Now, how does the brain know to connect single cell to amoeba? Well, because in the learning episode from reading the book, the concept of amoeba was being activated. So while the hippocampus was making a distinctly new memory trace, right, in the cortex, the concept of amoeba will be activated. And so this new information can be linked to recently activated relevant concepts, and amoeba is the relevant concept. So now here's where consolidation comes in. System consolidation will help to integrate this new information into the semantic memory system. We're going to attach the new information to our concept. So you see, the hippocampus will go through that replay process, and that replay happens after learning, also during sleep. And what that will do then is strengthen the cortical memory trace for the new information. Initially, that information was weakly connected to the concept of amoeba, but after consolidation, we strengthen that connection. So we've added some new information to our concept of an amoeba. The prior existence of the concept amoeba allows the brain to quickly add new information. And this is kind of an interesting idea, that knowing more things makes future learning more efficient. If we already have information about amoeba here, it's easy to attach new information to already existing concepts. So it's kind of like the more you learn, the easier it is to learn more. And sometimes the new learning involves inhibiting previously established links. So for example, early on we might have incorrectly learned that amoeba are animals. They're not. They're single-celled. And so we can think of then this consolidation process as not only introducing new information into our semantic memory network, but updating links that are already there. We can inhibit previous links as we learn that amoeba are not animals. So there are two kinds of retrieval then. Episodic retrieval requires the hippocampus. If I can retrieve the circumstances of learning, like the information I learned on the microscope versus the information I learned from reading a book, then I have two separate episodic memories. But often we forget the circumstances of learning. Nevertheless, if the consolidation process was successful, we should have lots of information in our semantic memory system that can be accessed from other cortical memory retrieval systems. And so again, in a school setting, we want to effectively transform episodic learning, the kind of learning happening in classrooms, into long-lasting semantic memories. Being educated means having lots of information in semantic memory, but of course it got there from episodic memory.